So this video is more just, you could say, for myself, because I thought it was an interesting connection that I saw between really, I guess, block ciphers in cryptography and quantum computing. And it comes from the fact that you need reversible computing. And so the problem is that in cryptography you have a lot of stuff, a lot of primitives like these things called one-way functions. And you have, you could call it pseudo random functions. And you could say families if you're being technical with it. And pseudo, I shouldn't put it in parentheses. We do keep the pseudo in there. Random permutations, etc. And we use these things, these are sort of our building blocks that we put together a lot of cryptography on, and with this we can actually do all symmetric cryptography, which is if you have a shared key, you can send messages back and forth in a secure way. But the question is, how do we get from here to here? Well, maybe first I should tell you what these two things are in case you don't come from a cryptography background. Well, what's a pseudo-random function? Well, in an ideal world, we would be able to summon a function f, which we can compute with a computer, that lets us go from, I like using this notation often for bits, from n-bit strings to n-bit strings. That is fully random. If we could do this, you could imagine, and we'll say it's keyed, and so we have a key. And so you could rather easily make some sort of encryption scheme with this. If you and I share the same key and nobody else knows it, well, I take my message M, and all I do is I take an addition of S with fk of 1. And this being a random function, so a purely random function, what does that mean? That means for every single input, you get a random string on the other side. And so if you know some information theory, if the key space is small enough, you already know this is impossible, because you would need the information involved here would be n times 2 to the n bits, and the key space key will be some polynomial in n bits. And so this is an impossible thing to do. But let's imagine we could do it. Let's imagine, cross our fingers, summon hope, we can do this. Well, then I could do a very simple encryption scheme. I just, I do this, and I send it on its merry way to my friend, and my friend gets a ciphertext C, which is equal to this, and just computes the same function, same decryption and same encryption function. They have a secret key K, and they will get that this equals M. A very easy way to do a sort of stream cipher. But another idea for various reasons is that maybe we want a pseudo-random permutation. And so I'll write this pk. And what this will be is it will be something that's like a random function, but it's actually a permutation on these two inputs. In practice, all we need is that, maybe this is some poly in n, or maybe it's just like 2n. In practice, we actually just require that this be something that why am I blanking out? That is injective rather than bijective, but we can achieve bijective. And the question we have here, which we will answer, is how do we get, because we can construct from one-way functions pseudo-random functions, so it's not exactly a random function, but the idea is that if we sample keys from our key space, we can't tell the difference between this function and a truly random function in a reasonable amount of time. And this is how a lot of cryptography is based, is that if we could do that, then we could break a one-way function, which is sort of like a random function, but it's a weaker condition. And so we bootstrapped our way up from one-way functions to pseudo-random functions. The question is, can we bootstrap our way up from pseudo-random functions to pseudo-random permutations? And to be clear, this is not, by a permutation, I don't mean an n by n permutation, where I'm just permuting the bits. That would be very easy to crack. I actually mean, to represent it fully, it would be a 2 to the n by 2 to the n permutation matrix, because it's permuting all these 2 to the n bit strings. So the question is, how do we somehow apply this random function, which will not be injective, or won't even be close to being injective? You can do an argument with the birthday problem that every square root of the space, so every 2 to the n over 2 inputs, you should expect to see a collision. And so the question is, how can we sort of rot from this, or from a family of these, something that's a permutation? Well, let's say you're working on this problem and you get distracted, and you have to go to your quantum computing class. You're in your quantum computing class now, and they teach you all these things. Maybe your quantum computing class is not that great, and it was like my lectures, which were not that great. And they show you that, like, oh, we have these states, and there are these things called, like, superpositions of psi or whatever, and then we do these operations called unitary matrices, but every operation prior to measuring is invertible. But we want to be able to do classical computation with a quantum computer. And this is a problem because so many classical functions that we do all the time are not invertible. They're like pseudo-random functions, which aren't invertible. So how do we do it? Well, they show you this trick. They say, well, it's not invertible. Say we have some classical function f we want to compute. And so we want to go from, some input, which we write in this silly way, x, and we want to go to f of x. Say again, it's n bits to n bits. Okay. Well, you can't do that. That's not invertible. But you can do this. What if you have memory? Instead of going from this to this, you go from this, just 0 a bunch of times, a 0 register, to this. Now this is invertible, and it is unitary, and it maybe for the details of f of x, because we break it up into a circuit, we have even more 0 bits we use. And so there might be some bits being used elsewhere. But this is a way that we can sort of compute x, f of x, while keeping things invertible. And it's very interesting. You just say, instead of, we take the circuit where we compute f on x, and we take its sum with the second register. And how is this invertible? Well, what if we did that operation again? So the operation precisely is not exactly this. It's actually x, y. We'll do maps too. We'll keep it all in LaTeX this time. Goes to x, and then y, o plus f of x. So this is the actual map we're doing. If we put y equals 0 to the n, we've computed f of x. Well, if you apply this map twice, you notice you'll add f of x to it again, and you'll get back to xy. And so we've somehow did a non-invertible computation in an invertible way. And you stare at this and you're like, hey, this looks interesting. What else can we do here? And you come back here and you're like, okay, well, say I have fk of x. And maybe I'm going to make, I'll double the size. And like, well, what if I try the same trick to make a pseudo-random permutation? Well, I have x comma y, and I map it to x and fk of x, o plus y. And you're looking at this and you're like, well, this is clearly not something that looks like a pseudo-random permutation. For one, if I look at the first bits and I know fk, I can always invert it. Or at least I always learn a lot of information this way. But what if I applied it twice? Well, if I apply it twice, this happens. and we don't get that far. But you have one more idea, and this one more idea is what leads to Feistel networks. Let's call this trick, I don't know, invertible F. So you're like, okay, if I do IF twice, I guess I should write it with a capital F because we're doing capital F. If I do IF twice, that does nothing. But what if in between I swap? So the swap map is very simple. I just do xy maps to y comma x. What happens if I do that? Well, let's map out the inputs. We get xy goes to x comma fk of x plus y. Then we swap these two. So imagine I swap these two. And then let's apply the same map again. Well, then we'll apply if right here. What do we get? Well, because this swaps and stays the same, we get fk of x. I should write in latex fk of x, o plus y, comma, and then this gets to be a bit of a bunch of stuff going on. So let's see if I get this correct, because I feel like this is where I could mess up. Backslash o plus y. And you look at this, and it looks a lot harder to invert. Just sort of by the eye text. Oh, not o plus y at the end there. O plus x. Let's see, did I do that right? You swap, you add. Yes, that looks right. Because now, originally, when you use the if to invert, you have this x tag that lets you invert it. Now, you have this here. And the thing that lets you sort of semi-invert is that you can still apply this. Well, you've still done an if. But when you're looking at this as a joint function, you start with x comma y. And now you need fk of x plus y. Well, let's see. If you have the output here, you can still apply fk, and you can add this, and you can still recover x. But it's already kind of difficult to get y. And so you can recover x, so it doesn't look all that random. But the idea is you literally do this a third time. You swap it, and then you do if. And so basically, what it looks like as a map is if, swap, if, swap, if. To get this pseudo-random permutation. So here, if you see the output of this, you can still apply fk, and you can still recover x. And then once you've recovered x, can you recover y? Well, yes, you can apply fk to that. And you can keep going back and keep going back. But if you do it a third time, the argument, and I actually forget if there is a rigorous kind of hybrid argument to do this, is that you get a pseudo-random permutation. You know that if, SIF, SIF, all of these are permutations. But if you go 3 times over, you will get a pseudo-random permutation. If you go 16 times over, this actually 16 times over, this gives you a version of, this gives you the pseudo-random permutation used in a lot of symmetric ciphers, namely DES, which again, you don't need a pseudo-random permutation, but we use it for various reasons instead of a pseudo-random function. I wonder why they chose to use pseudo-random permutations. Maybe just because it was early and it feels safer if you're using something reversible, because you actually don't use the inverses of these permutations. Do I want to calculate out this third iteration? Sure. Let's do it. Let's write out the third iteration just to see how kind of ugly it is. So that's one thing. O plus fk of x, O plus y. Because we swap these two, and then we add that to that, And then we just have, this is the output of the third iteration. That if we do it yet again, and imagine doing this 16 times to get some monstrous looking thing. Is this what we get? Fk is this. Yes, you can apply Fk of this, and you can get Fk of x plus y back. But once you get Fk of x plus y, then what can you do? Now you just have Fk of x plus y and nothing else. How are you going to invert further? But we do this thing 16 times, and if you do such a thing 16 times, that's what a Feistel network is called. So I just wanted to do this video specifically. I wonder how long I've been going, because it's an interesting connection between the problem of reversible computing that you get in quantum computing and this way to go from non-reversible computing to reversible computing to show that these primitives in cryptography are equivalent.